Hi, my name is Wu Lue. Today, I will be introducing to you about this fascinating project, deep learning approaches to predict clinical outcomes of cancer patients from multi-omics data. Cancer, it caused 8.8 million deaths in 2015 alone, contributing to 15.7% of total deaths of that year. It is a truly devastating disease. But what if we are able to predict the clinical outcome of cancer? Firstly, we can help the doctor to give different treatments with regard to the status of cancer of the patient. For patients, it also helps them to be more informed about the possible outcome of their disease and therefore prepare a better, more appropriate plan for themselves. It can even help review the possible causes of cancer, as we always try to identify the most relevant biomarkers of each patient. The word multi-omics simply means from different subtypes of biological entities, for example, transcriptome, metabolome, and proteome. They contain information of the patients, both individually and combined, because of the possible interactions between different biological entities. By studying multi-omics data, we are able to identify and pinpoint relevant biological markers, and thus help with the study of cancer. The problem, however, of using multi-omics data is the small n large p problem. This problem refers to the fact of multi-omics data having few samples but very large dimensions. This project tries to overcome this problem using various techniques. How? By first building a patient similarity network. Using each omics data, we build a network where each node is a patient and the ages are the Pearson correlation coefficients of patients. The Wilcoxon analysis, also known as the Wilcoxon sign rank test, tests the null hypothesis that two related paired samples come from the same distribution. In other words, it allows us to identify the most relevant features out of the huge amount of features we have. Next, Pearson correlation coefficients are calculated using this formula to find the linear correlation between patients. The weighted gene co-expression network analysis then rescale and normalize the network into a scale-free network, which has its degree distribution following a power law. From the PSN generated, topological features are extracted to further reduce the feature dimension. Centrality features are graph properties of each patient in PSN, like closeness centrality. Modularity features are obtained by finding optimal number of modules by clustering and transform the module's membership into a binary feature. In order to deal with multi-omics dataset, two methods are used to combine datasets of different biological entities. Firstly, feature-based fusion. In this method, we are trying to combine the multi-omics data in a feature level. For each omics dataset, we are able to generate one PSN. After extracting the features from the PSN, we are able to combine these generated features and use the concatenated features as input to train our neural network. Whereas in network-based fusion, after building PSN for each omics dataset, we use similarity network fusion to fuse the PSNs iteratively into one network. Then, the topological features are extracted from that network to train the neural network. Working on neuroblastoma dataset with gene expression data and methylation data, we achieved great results. Both methods introduced achieved improvements as compared to baseline method using support vector machine, indicating the methods are effective. Thank you for watching. I hope you have enjoyed the video.